This is video number 3 on the integrated rate law, with this one being on second order reactions. Remembering that a rate law is nothing more than a mathematical method to determine how fast a reaction will occur under a specific set of circumstances. We have the differential rate law, which is concentration versus rate, and the integrated rate law, which is concentration versus time. For a zero-order reaction, the differential rate law is rate equals K. The integrated rate law is A sub T minus A sub O equals negative KT. The rate constant K is the negative slope of the line, or the absolute value. The half-life is not constant. It varies with the concentration. So if you have a constant half-life, it cannot be a zero-order reaction. However, if you do not have a constant half-life, it doesn't mean that it is zero order. For a first order reaction, the differential rate law is rate equals K times the concentration of A. The integrated rate law is the natural log of the concentration of A at time t minus the natural log of the concentration of A at time 0 equals negative KT. Once again, the rate constant is the negative of the slope of the line, or the absolute value of the slope. And the half-life for a first order reaction is constant, and so if you have a constant half-life, it must be first order. If you don't have a constant half-life, it cannot be first order. So second order reactions. Here the differential rate law for a specific reactant would be rate equals K times the concentration of A squared. The integrated rate law here is 1 over the concentration of A at time t minus 1 over the concentration of A at the beginning equals positive KT. And here the rate constant is the slope of the line, which I guess technically is the absolute value. And the half-life of a second order reaction is not constant. Just like zero order, it depends upon concentration. So let's take a look at butene dimerizing to form octene. You run the reaction and you get this data. What is the rate order of this reaction? You start with, is it zero order? You either have to graph it out or the down and dirty, check the slopes. So I look at 0 to 1600 minutes. I get a slope of negative 3.1 times 10 to the minus 6th. I look at 1600 minutes to 3200 minutes, and I get a totally different slope. Since I have different slopes, this cannot be a straight line, so it's not zero order. Now I check, is it first order? I add a column with the natural log of the concentration of the butene. I cannot use the half-life to see if this is first order because none of the concentrations here end up being half of a previous concentration. So we either have to graph or check slopes. I'm going to go with the down and dirty, check the slopes. I'm going to use 0 to 1600 minutes first. Then I'll go 1600 to 3200 minutes. It's obvious there are two very different slopes, so it is not a straight line. Therefore, it can't be first order. Is it second order? And you're not allowed to say because it's not zero order and it's not first order, it must be second order. You still have to prove it. So now you have to add the column of 1 over the concentration of the butene. Now you graph or check slopes. 0 to 1600, you get 0.06125. 1600 minutes to 3200 minutes, you get the same slope. The slopes are the same, so the graph is a straight line. So this is second order. And the K here is 0.06125 per molar per minute. So to review the integrated rate law, it will compare concentration with time. Concentration of A sub t is the concentration of A at a specific time t. Concentration of A sub 0 is the concentration at time 0, or at the very beginning of the experiment. T is equal to time in whatever unit is given. K is the rate constant, and you will need to use units with that. And T1/2 is the half-life, the amount of time it takes for a concentration of a reactant to decrease by 50%. For a zero-order reaction, the graph of the concentration of A versus time is a straight line. This is the integrated rate law, and K is equal to the negative slope, or the absolute value of the slope. And finally, the half-life is not constant. For a first-order reaction, the graph of the concentration of A versus time is not a straight line, but the graph of the natural log of A versus time is a straight line. The integrated rate law looks like this. K is equal to the negative slope, or the absolute value of the slope, just like for zero order. But for a first-order reaction, T1/2 is constant and can be used to identify a first-order reaction. If you have a constant half-life, and thus a first-order reaction, then the half-life is equal to 0.693 divided by the rate constant. For a second order reaction, the graph of 1 over the concentration of A versus time is a straight line. This is the integrated rate law, but this will be a positive slope, and so the value of the rate constant is equal to the slope. And once again, the T1/2 or the half-life is not constant, so if you have a constant half-life, it cannot be second order. So now we have covered the differential and the integrated rate law. Upcoming videos will delve more into the actual mechanisms of reactions.